Okay, so here's the next problem. It says number three. What is the rotation rate of a point on the equator of a planet if the radius of the planet is 65,723.7 kilometers, and it takes a point on the equator to rotate one complete revolution in 8.3 hours? Um, we want the answer in kilometers per hour, and it says to round to one place past the decimal. All right, so there's and of course there's the answer, 49,753.5. All right, so let's see how we get that. There's only really only one trick with this one. If you have something in a circle, or and you know the radius, that's not the middle, but let's say that this is the middle of the circle. So if you know the radius of the circle, there's a relationship between the circumference, which is the distance all the way around, and the radius. All right, and so the circumference of any circle, this is just universally true, is equal to 2 pi times the radius. All right, that's just a standard thing. Uh, for all circles, that's just always true. All right, and so the idea here is, what's the velocity? The velocity is, of course, the distance divided by the time. Or in this case, it's divided by the period. So this is really the distance that a point travels, is really the circumference, right? That's what. So let's write the circumference in terms of what it is, with values that we know. So it's going to be 2 pi times the radius, which they give us in this particular problem is six point six. Sorry, 65. I really messed that up. 65,723.7 kilometers. All right, so that's that, and then they give us the period as 8.3 hours. 8.3 hours. And see, notice the answer will be in kilometers per hour, which is exactly what they require in the problem, right? It says kilometers per hour, one place past the decimal. All right, so we just have to put all this in our calculator, which I just did, but I'll redo it again. So let's lower that down a little bit. All right, so here, let's clear this. All right, so it's going to be 2 times pi. All right, so there's the 2 pi, and then times 65,723.7. All right, so that's the radius of the planet, and then we divide that by 8.3 hours. So it takes a point on the equator, 8.3 hours to rotate around once, and so we divide by 8.3, and and of course we're rounding this to one place past the decimal. All right, so 49,753.5. The next digit is a 1, so you don't round up. All right, which is exactly what I have right here. All right, so that's number 3. All right, so here's number 4. It says find the mass of Jupiter from the following data table, and it says round to one place past the decimal. All right, so we have a satellite of Jupiter. It's actually the largest moon in the entire solar system, called Ganymede. And it gives us the size of Ganymede. It gives us the distance from the planet, in thousands of kilometers, and it gives us the orbit, and also the mass of the moon. I said planet a minute ago. I'm sorry. I meant moon. Ganymede is a moon of Jupiter. All right. So anyhow, the way that you do this is really the only thing. We don't need this information, right? The radius of the moon does not matter. All right. So we don't want that. we do want the distance from it. So that's that number right there we're going to use. And we also need the orbital period. All right. We don't care about the mass of the moon. We don't care about the density of the moon. All right. So the purpose of this is to understand what you need to do. All right. And so you really just need the orbital information. And so we're going to use the modified version of Kepler's third law. The mass is equal to 4 pi squared times the distance from the distance the whatever the object is that's orbiting, the distance it is cubed divided by big G, which is of course the universal gravitational constant. It's always the same number, divided by the period squared. All right. So the only thing about this is R has to be in meters, which it's not. You notice it's in kilometers. And then the period, P, has to be in seconds. All right, so we got to convert to meters and seconds. So that's really, and then we're going to plug it into this formula, and that'll be it. All right, so R is, let's see, so it's 1,070 times 10. So it's times 10 to the third, right? E3 kilometers, right? But that's easy, very easy to change to meters, because I know that in 1 kilometer there are 10 to the third, 10 to the third meters, right? So the kilometers cancel, and so 10. So this is 10 to the third. This is 10 to the third. So this becomes 1070 times 10 to the sixth, right? All you do is you add it's 10 to the third times 10 to the third. You add the exponents, meters. All right, so that's what we're going to use. And then the period, now that we'll need a calculator for. So the period is 7.155. That's a point. Days. And we know that in one day, there's 24 hours. In 1 hour, there's 60 minutes. And in 1 minute, there's 60 seconds. All right, so that, so the minutes cancel, the hours cancel, the days cancel. All right, very nice. So let's calculate that, and we'll store that number, and we'll use it in just a second here. Oh, that was the last problem. All right, let me clear that. All right, so here we go. So 7.155. It's a very precise number. That was actually measured using a spacecraft that orbited Jupiter for a long time called Galileo. It was the Galileo spacecraft. Anyhow, times 24, and then times 60 squared, or times 60 times 60. So it's that many seconds. All right. So I'm going to need that. I'm going to store that in my calculator. So 618,192 seconds. All right. So that is now stored in my calculator. See, there it is. All right. We'll come back to that in just a little bit. All right. So I've written all the important numbers here. It is the conversions that we did in already. So there's R 1070 times 10 to the sixth meters. We got to cube that, multiply it by 4 pi squared, divide by big G, which is this number right here, 6.67 times 10 to the minus 11th. And then remember, we found the period in seconds. That's this number here, 618,192, and we square that. All right, so let's put all that in our calculator. Remember, I've already stored this, which is the period. All right, so all right, here we go. All right, so all right, this is going to be 4 times pi squared times, so it's 1070 7, 0 times 10 to the 6th. All right, but I've got to cube that, so I use this x to the y button. All right, you got to know how to do that on your calculator. Raised to the third. All right, and then now I'm going to divide that by 6.67 times 10 to the minus 11th. All right, so now this is not going to be the complete answer. This is so what I just calculated is just this part of the equation. All right, now I have to divide that by the period squared. All right, so divided by, and remember I stored that already. There's the period. I square it, and that is going to be. Let's see what it comes out to be. All right, so this turns out to be 1. You can't tell that here, but this is 1.9, right? Because it's 1.8. It's 1.897, right? But we're going to go one place past the decimal, so it's going to be 1.9. 1.9, and I've done this already, so I already know that it's times 10 to the 27th kilograms. All right. Now, how do you can count the decimals here? Let's go back to my calculator. This is why you kind of need to just have a calculator that'll change it into scientific notation automatically. But look, if I divide this number that's in my calculator, this very large number, by 1 times 10 to the 27th, I'll get 1.897. 1.897. All right. So let me just show you this, just to prove it. So divided by 1 times 10 to the 27th. All right, and that turns out to be the 1.89. So I'm going to round that to 1.9 times 10 to the 27th. All right, so that is the correct answer, which is the number that we had when I first started the problem. So that is what was that, number 4?